Recording. Okay, hope all of you are doing well. Before I start, do you have any questions about anything about the course or the lecture or about, and now that we are 2 weeks past, hopefully things are pretty settled down. Okay, and I think yesterday was the last day to drop classes, so now we can take my true colors. Okay, I just took the liberty of writing down a few things from Magic, just so that I don't have to write them all over. Like, you don't have to copy them frantically. It's all things that you have seen last week. I know it's a lot of information. Okay, so we were talking about the spring mass dashboard system, which was with the external force. That's where we stopped. Okay, but then we started off with just the spring and the mass first. Okay, that is where we had simple harmonic oscillation. Okay, then that was a good place to even introduce the amplitude phase form. Okay, so these are the different cases there, and then we brought in damping, and that is where the motion of the system either got immediately stopped, okay, as in cases A and B where there was no oscillation. Case C, there is some oscillation that kind of dampens down because of the P being negative. Okay. And once again, I mentioned this so many times, that is the natural frequency without damping. With damping, it's a slightly smaller frequency called the pseudo frequency. Okay. So depending on the values of C square and 4mk being greater, less, or equal, there are those three cases which are kind of non-overlapping. You cannot have both overdamped and underdamped at the same time. Okay, it's a trichotomy there. And we started doing external force, which is an application of 2.5 non-homogeneous differential equations. Yeah. And the external force we are talking about is either a cosine or a sine. So the typical guess would be both cosine and sine with the same alpha there. Alpha is the frequency of the external force. Okay. And we also talked about the transient and the steady periodic parts of the solution. Transient is when, as t goes to infinity, that solution is dying down. Okay. The steady periodic part does not die down as t goes to infinity. So those are the additional things that you have to keep in mind. Okay, you're not only just solving the differential equation based on 2.5, you're also trying to get a lot of other things there. Okay. So I'll leave it here for some time. It said these lectures are recorded. Okay, you don't have to write down these things unless you see something brand new there. I don't think there should be anything new. Okay. So that's where we stopped. Let me just write down that example we were doing last Thursday before we stopped, so that I can mention a few more things based on it. So if you started doing the homework, the only changes are just the numbers that you get for MCK. Okay. There's not a lot of variety in there. So example from last Thursday. Not going to do the whole thing. Okay, that's going to take another half an hour. X double prime plus 2x prime plus 5x equal to 26 sine of 3t with the initial conditions of x of 0 equal to -1 and x prime of 0. And the solution that we got after around 25 minutes of struggle was this. X of t. That's not too bad. You just have to kind of do it step by step. Okay, find xh first, then find xp, plug in the initial values, and you get e to the power of -t times 2 cosine of 2t plus a half sine 2t minus 3 cosine 3t. And there is no need to copy this down. Okay, it should be in your notes if you were here on Thursday. I'm just writing the final answer, -2 sine 3t. That's where we stopped, and I mentioned that this is the transient part because e to the power of negative t goes to 0 as t goes to positive infinity. Okay. And this is the steady state or the steady periodic solution. I hope you got a chance to at least try some of the homework questions, and you may have seen that those questions, most of them ask you to write the steady periodic part in the amplitude phase form, okay, which I did not do on Thursday because we kind of ran out of time. Okay. So that's where I'll start, and then we'll talk about resonance and move on to chapter 3. Okay. So I hope by now people are in here. Before we start, again, we make sure that any questions, can people hear me online?
Yes.
All right, thank you. Okay, so let's start with this example. Okay, write the steady periodic part of the solution in the amplitude phase form. Okay. The same example. Okay, we only did one example from 2.6. So steady periodic part in amplitude phase form. Well, there's only one amplitude phase form. Okay, whatever I've written up there, that is the general format for any amplitude phase form. The only thing now is to just manage your C1 and C2 cleverly. Okay, you just need to be careful about what you call as C1, what you call as C2, and what you call as the frequency term here. Okay. So I know that you obtained these as your A and B when you solved it, okay, but nobody's going to get offended if you call them as C1 and C2. Just for the purpose of this question, let's just call this a C1 and this is C2. That way you don't have to kind of reformulate a whole bunch of things and make it more complicated. Okay. As long as you preserve the C1 for the cosine and the C2 for the sine, whatever you did earlier for your amplitude phase form is still true. Okay. Because the math doesn't know that you're doing two different functions. Okay. All you have to do is just preserve the positions of those terms and you're done. So C1 is -3 and C2 is -2. You might be thinking, oh, I had C1 equal to 2 and C2 equal to 1/2. That's where it's don't look at that, right? We just need to focus on this. So C1 is -3, C2 is -2 for the steady periodic part. Both are negative, sadly. And that negative thing is important for fixing the value of phi in the respective quadrant. Okay. Amplitude is still positive, square root of -3 square plus -2 square, square root of 13. And phi is the arctan of C2 over C1. Now, since both are negative, there is no need to be confused here. It's going to be the third quadrant, and based on what I wrote up there, it's going to be just plus pi. Okay, but these both are negative, so you're adding a positive number effectively. Okay. So that's because both are negative. And that's equal to tan inverse of C2 over C1, which is -2 over -3, which is positive 2/3. 3.14. Okay. You just need to take a calculator and do that out and tell me what that is in radians. Okay. Anybody who could? 0.73. All right, looks sensible. Because 3.14 plus a positive number. Okay, 3.73. So the amplitude is there, the phase angle is here, okay, and the only thing that remains is this. This is your alpha, which is the frequency of the forcing term. Okay, so when you write the amplitude phase form for the steady periodic part, you're going to make use of this alpha for the frequency. So this would be a cosine of alpha t minus phi. A is the square root of 13. Cosine of alpha, which is 3, that is what the question gave you. Okay, this 3. That 3 is, this 3 is, this 3. Okay. Minus phi, which is 3.73. And that is your steady periodic solution, which I think our textbook sometimes uses as a subscript x SP of t. SP for steady periodic. So if you saw something mysterious in the homework, this is probably the only thing, okay, which should take care of most of the exercises in section 2.6. Also note that when the question says the system starts from equilibrium, that is given for a purpose, that's to let you know that your x of 0 and x prime of 0 are both equal to 0. Which I think should be obvious that when it's at equilibrium, it's not moving up or down, there is no velocity. Okay. This can only apply when there is some external force. If there is no external force and if you don't do anything, the system is not going to move. Okay, just common sense, right? Newton's first law of motion. So this is only applicable if you have an external force to kick it and make it move. Okay. All right, so in terms of the heavy problems in 2.6, this is what it looks like. Okay. Any questions on the steady periodic part amplitude phase form? Or all right, now I'm going to erase all that stuff there. Okay. Here is a question for you, if you don't have any questions for me. Suppose we get back to our spring mass, no dashpot. Okay. A, this is M, C equal to 0. Okay. And suppose I apply an external force here, F of t equal to F naught cosine of omega t. So I'm purposefully using this omega here, not alpha. Okay. You know what omega is based on this. This is the same omega here. Okay. So omega is the natural frequency. And I'm applying this external force. Okay. And the system starts from equilibrium or something. We don't care. Okay. Can you write the xp for this one? You don't have to solve or anything, just write the initial guessing function for the particular solution xp. This is the differential equation we are talking about. Okay. Case with regard to c equal to 0 in the equation that we had somewhere here earlier. Okay. So the homogeneous solution xh would be c1 cosine of omega t plus c2 sine of omega t. A simple harmonic motion, right? And then I'm applying this external force with the same frequency here. Can somebody tell me what XP would be? Somebody online or somebody here, just, yeah. All right, so A cosine omega t plus B sine omega t. I don't know why I left that gap there, but xx is what you would have done if the variable was x here, right? T. If you're writing y in terms of x, you can write ax cosine omega x, but you're writing x in terms of t. Okay. This is not a simple harmonic oscillation anymore. Okay. This is simple harmonic oscillation. So this will just oscillate to the same amplitude forever. Okay. What about this one? As t increases, okay. So at t equal to 0, it starts at 0. Because both these terms are 0, but as t increases, it just goes crazy. Okay. At some point, you will hear a noise of the spring breaking because it cannot sustain that vibration anymore. Okay. So there is increasing amplitude of vibration or oscillation. Eventually leading to structural failure. This mechanical property of mechanical phenomenon is what you call as resonance. So here the resonance is between the external force, which is having the same frequency as the natural frequency of the system. Okay. So this omega here is equal to this omega, which is already part of the system. Okay. Frequency of the external force. And that's equal to the natural frequency of the system. It's a very important concept for engineers because when they design, especially mechanical systems, you have to be careful to avoid these kinds of coincidences where the frequencies match and can create all kinds of problems. Okay. For our purposes, it's just to kind of be familiar with what it means. Okay, we are not doing any complicated examples with resonance. Okay, all you have to know is this: resonance means the frequency of the external force external force is equal to the natural frequency of the system. This is not the only place where you would see resonance. Okay, there are lots of examples in engineering and in nature where resonance is applied. Okay, if you go on YouTube and search for resonance, you'll see a lot of cool videos about it. So one video would be if you have somebody singing at a very high pitch. Really loud but shrill, okay, at a high pitch, and if there is a wine glass sitting right next to it. Okay. At some point, the wine glass will start vibrating at really intense frequency. That's because the oscillation just grows and grows and grows. It cannot hold it anymore. it'll just break. Okay. So that is one example. Not everybody can do this though, because you have to sing at a really high pitch. Okay. I think the more popular example is this. Okay. There was a bridge in Washington named Tacoma Narrows Bridge. And this video is still on YouTube, I think. So, and since nobody got killed there, it's a pretty fun video to watch. Okay. It was a very windy day. So the wind was really strong and the bridge just started oscillating, okay, just like a simple pendulum. And at some point, the bridge just collapsed. Luckily, nobody died. So that was a video that people could kind of enjoy watching. Okay. So that kind of tells you why resonance is something that you should avoid in the case of mechanical systems. But there are also nice applications for resonance. So tuning of radio stations, for example. So if you are using a knob, as in the old-fashioned radios, you are trying to match the frequency of the incoming radio signal. So that's a resonance there. Okay. Or even in your daily microwave ovens. The microwave in your microwave oven has a certain frequency of its own. Okay. So the frequency of the microwave it should resonate with the frequency of what, do you think? So you're warming up pizza or some frozen vegetables or, you know, the water in the food, because the food could be all kinds of stuff, right? So the common ingredient of most food items is water. So the frequency of vibration of the water molecules. Okay. Another example is if you go to a play field and use a swing. Okay, you keep pushing somebody on the swing, and at some point it will just start oscillating. And if you are just pushing at the right thing, you don't have to even push really hard. You just need to tap it because the oscillations have hit the natural frequency, and you're just giving the same push as the frequency of the system. So those are all nice observable applications of the concept of resonance. Okay. All right, so if you look at the exercise in 2.6, you might see questions like this. Okay. It could be a little silly, but that's all we are doing in this course. So, okay, for example, consider a system where m equal to 1, k equal to 4, and f equal to 3 cosine of omega naught t. Okay. For what value of omega naught will there be resonance? Okay, so that's the worst possible case you are really seeing in this course regarding resonance. You're not going to talk about how the bridge collapsed on a particular day in Washington state or anything. So the answer again is based on when this omega naught would be equal to the natural frequency of the system. So it's omega naught equal to the square root of k over m equal to square root of 4, which is 2. So it should be a pretty easy exercise in this course, but if you're taking a course in vibrations later, okay, it's a very important concept, and I hope you will remember where it all started. Okay, so that is the official end of chapter 2, and up to here for test number 2 this week. Okay. Yep, up to here. So do the homework, and you should be in good shape for test 2. Okay, I think in the announcement I mentioned what kind of questions I would expect. I don't see any reason why you should run out of time or anything if you practice all the things we have done in class. Okay. Any questions before we move on? Okay, let's move on to chapter 3. I think I posted something on Canvas, which, let me remind you, if you are here, I would require you to open it electronically or have a printed version of that with you. Without that, it's not going to work here. Okay, so if you have a laptop with you or some kind of smartphone or something, please open Canvas, open modules, and we need that Laplace table. Okay. For those of you who are online, I think I've written that in the chat, so just make sure that you have it. So you don't have to do it in a hurry, as you know, we'll slowly reach there, but at some point you need it. Okay. All right. So chapter 3. The name of the mathematician who did this was Simon Laplace. Okay, it's not Laplace, it's Laplace. Okay. So I know it looks like replace and misplace and displace. So Laplace, it's Laplace. Okay. So when he did this, actually, he didn't know how important it was going to be in future applications. It's pretty cool, and it's kind of mysterious as to how this really takes care of all the differential equations we have done so far in a much quicker way, if we are good with algebra. Okay. So that's a big if there. So this is a purely algebraic concept. So the calculus is kind of behind the scene. And the reason why this works is because of the following. The students always ask, why does this work? Okay. Yes, once you reach electrical engineering and control systems, this is all over the place. So there should be a reason why it is so effective. Everything that you have seen so far, okay, these are the 3 main behaviors that you have seen so far. Okay. Exponential decay. If you look at the spring mass dashboard system, okay, exponential decay, sine, cosine. So we have e to the power of some negative at. This is cosine of bt. Oops, this is sine of bt. This is cosine of bt. Almost all the physical processes, especially if you are working with signals, okay, these are the 2 types of signals that you're going to come across all the time, sinusoidal signals. Okay. And you also know that e to the power of I times bt is cosine of bt plus I sine bt because of Euler's identity. So the concept of Laplace transform is based on combining all these into a single term. Okay. If you take any function f of t and multiply it with a function that combines an exponential decay and a sine cosine term, okay, which is going to look like this, negative a plus ib times t. So that has both the exponential decay and the sine and cosine terms. Okay. And if this is your incoming signal, then you can transform this in terms of time. Okay. So it's an integral transform, which means you're taking this function and getting something out of it. Okay. And I'll tell you what exactly you're getting out of it. So you're taking this function, multiplying with this, and getting this new creature out of it. Okay. As t goes from 0 to infinity, this is what we call as an integral transform. It's called a transform because it is changing this function into something. It's transforming into something. Okay, it's an integral transform because it's an integration process. So this is the background calculus that is happening, which you probably won't be doing in chapter 3 because it's already taken care of. Okay. What does it really do? it takes a function or a signal in the time domain. You're always going to assume that your time is in the positive direction. So this is going to be starting from t equal to 0 to infinity. Okay, that is our assumption. You could also do it from negative infinity to infinity, but for this course, we'll just assume it's positive, okay, without losing any generality. Taking this time signal and breaking it into two components, the real and the imaginary components here. So you're going to get a new function, capital F of S. Okay, S is the frequency term. It's an imaginary or a complex frequency. So we're going from a time world into a frequency world. Okay, that is what Laplace transform does all the time. Okay. Things are easier to understand in the frequency world because it is broken down into its amplitude and phase. Okay. The time world is kind of complicated. It's just one dimension. The frequency world is two-dimensional. This has got both amplitude and phase. Amplitude. So it's easy to kind of understand what is going on in that signal, unlike this one-dimensional signal. Okay. And that is the magic of Laplace transform, which when Laplace did it first, he didn't do it for a signal, he just did it in a mathematical way. But later people understood, oh, this is cool. We could do this and get some useful information. So this is the basic background of Laplace transform. Okay, the reason why you do it, especially if you're an electrical engineer, you cannot live without this thing. So let's officially define this and see how to do this for the kind of functions we kind of generally come across in our math applications. If you need more information about this, and I'm willing to talk about it during my office hours, I don't want to get distracted with a lot of technical details about signals and so on. Okay. That is not the purpose of this course. But I hope I gave you some idea about why this is done. So get used to the two letters there, T for time, S for frequency. Okay, that's what we are doing throughout this chapter. So let's define this. Definition, let little f of t be a piecewise continuous function it doesn't have to be fully continuous. It could be piecewise continuous, which is one of the reasons why Laplace transform is so cool. Okay, it can be used to do problems which you probably couldn't have been able to do in chapter 2. So it's a piecewise continuous function defined for t greater than or equal to 0. Okay. So in some classes later, we might see things defined for negative t as well. It's just a simple extension of this. And assume that f of t is of exponential order. It's just a technical detail so that when we do this integration, it won't go out of bounds. Okay. To maintain convergence. You cannot find the Laplace transform of a function which is exponentially increasing with time. Okay, that is not going to be feasible. So you need to keep the function which is kind of well behaved. So exponentially decaying function is okay, sine is okay, cosine is okay. Then we define the Laplace transform. I'm just going to abbreviate it as LT for future reference of f of t. As I think the textbook or most textbooks use a script L like this. I'm not going to use that. Okay, I'm just going to use ordinary L after I write this. L of f of t equal to f of s. So this is the input, that is the output, and that's equal to the integral from 0 to infinity e to the power of negative st times f of t dt. Okay, so that s is the complex frequency I wrote earlier, the a plus ib term. Okay, so you don't have to worry about how the s is broken down to a and b. That is not something that we need to worry about. That's part of the process. Okay. So it's an improper integral. Okay, if you've taken calculus 2, the top limit is infinity. So we need to worry about when this converges so that the limit and the integral is well defined. Okay. When the improper integral converges. Improper, not indefinite, improper because of this. And it's for this convergence reason that I am insisting on the functions being within certain bounds. Okay. So throughout this chapter, we are going to input t and output s. Okay, s is the frequency. And before I start calculations, let me kind of show you why this is useful. Okay, so what we'll do in this chapter, starting later today or tomorrow, depending on how fast we go, is we take any differential equation. That is what we are trying to do in this course. Okay, take this Laplace transform. The magic here is that the Laplace transform will convert this differential equation into an algebraic equation. Some of you might be thinking, okay, isn't that a bigger headache? Actually, no. Okay. In theory, algebraic equations are expected to be easier to solve than the corresponding differential equations. Okay. But I understand if that is a subjective statement, so this is easier. But we are solving for s here. Okay, this is in terms of t. This is an algebraic equation in terms of s. So when you say easier, we are actually solving for s here, or solving in terms of s. Okay. Just write it here, solving in terms of s. But then our answer was supposed to be in terms of t. Okay, so we need to invert it or transform it back in terms of the time variable. So t to s to t. Okay, and this is going to be your solution. What are the kind of difficult parts of this process? It's usually this part. Okay, this algebraic equation to the transforming back. That is usually where you have to be algebraically well equipped to do this. Okay. Oh, s was the complex frequency. Sorry for not writing that down. Okay. So the differential equation from the t variable to s variable using Laplace transform, that's an easy thing to do. Okay. And then you solve it, which is also kind of easy, not too bad there. Okay. It's this part that is usually a little bit of a challenge, especially if you are not algebraically well prepared, and that's why I told you on the very first day that you need to know some partial fractions and completing the squares, all that stuff, so that we could easily handle this part. Okay. So this has some algebra involved. But our first task is to get used to the Laplace transform table. Okay, so we need to be prepared to read it from left to right and from right to left. Okay, that is going to be the first task, and then we will start solving these equations. All right, before we do that, do you have any questions about this? So keep the definition somewhere nicely boxed, okay, because we'll come back to the definition whenever we don't know something. Okay, this is where we will start. So if I don't know the definition of or the Laplace transform of some new function tomorrow, okay, that's going to be the starting point. No matter how difficult it looks, okay, there is no other place to start. Okay, so let's do some examples now. Let's start with the most basic function f of t equal to a constant k. It's a signal that is kind of steady in its amplitude. Right? So what is its corresponding Laplace transform? Well, I don't know, which means I depend on my definition. Okay, so Laplace transform of k will be integral from 0 to infinity e to the power of negative st times k dt. K is a constant, so you can pull that out. So it's k times. Remember that infinity is not a number. Okay, if somebody has told you that, that's wrong. Infinity is something that we use to represent something we don't know, right? We have to write it as a limit as some variable, say b, goes to infinity. This is how you have probably done in calculus 2. Okay, it's an improper integral, so you have to write it as a limiting case of some random variable. Okay, limit as b goes to infinity, integral from 0 to b of e to the power of negative st dt. Though in some cases I might get sloppy and you treat it as a number, okay, but at least in the first few cases I'll be respectful that infinity is not a number. Remember, t is a variable, okay, and the integral of e to the power of k t dt is 1 over k e to the power of kt. Here k is negative s. Okay. So it's going to be k times 1 over negative s times e to the power of negative st from 0 to b as b goes to infinity. So that's an s. Okay. When I write s, some students think it's a 5, it's an s. So it's 1 over that exponent and then the exponential function with t goes from 0 to b and b goes to infinity. All right, so let's finish that off. So that's going to be negative k over s times e to the power of negative s times b minus e to the power of 0, which is 1, as b goes to infinity. Okay. Don't forget that s is a positive parameter. We are living in the positive world, so there is no question of s being negative. Okay. As b goes to infinity, this term goes to 0 because you have e to the power of negative something. So what we have is negative k over s times negative 1, which is positive k over s. That's the first result you're seeing in Laplace transform. The Laplace transform of a constant k is equal to k over s. So if you look in your table, that is the first thing I've written there. Okay. It would be nice if you can just number those things in the table 1, 2, 3, 4, 5, 6 so that we can communicate easily. The case 1 is Laplace of a constant k equal to k over s, which means that the Laplace transform of 23 is 23 over s. Laplace transform of negative 17 is negative 17 over s, and so on. So now that you have the result, you can use it. You don't have to derive this from scratch. Okay. This is something you can use in all the problems from now on. Okay, so that's not too bad. Okay, so things get a little bit rough as you increase the intensity of that function. Okay, so example 2, f of t equal to some exponential function e to the power of at. That is, these are the basic functions that we talk about, right? The constant function, exponential function. Again, I don't know this, so LF e to the power of at. Eat is the integral from 0 to infinity e to the power of negative st times e to the power of at dt. I hope all of you know that it's not the product of the integrals. Okay. So you need to kind of combine these two into a single exponent. That's integral from 0 to infinity e to the power of negative s minus a times t dt. Once again, just don't forget your manners with infinity. Okay, so it's the limit as b goes to infinity. Integral from 0 to b of e to the power of negative s minus a t dt. So the same property of integrals that I wrote earlier applies here. Okay. So in this case, k is negative of s minus a. So this is going to be the limit as b goes to infinity, 1 over negative of s minus a times e to the power of negative s minus a t, and the limits go from 0 to b. So making use of my calculus 1 integral. And let me keep it on this side so that I could look up easily. So this is going to be, you can pull this thing out of the limit because there is no b in this term. Okay, that's going to be negative 1 over s minus a times the limit as b goes to infinity. Plug in the limits, it's going to be e to the power of negative s minus a times b minus e to the power of 0, which is 1. Now I have a question for you. What is the value of this term as b goes to infinity? Think carefully and answer. Okay, don't just give a sudden answer without thinking carefully about what is going on there. What is the limit of that? The second term has no b, so we are okay. The first term, as b goes to positive infinity. Just try your luck. I'm expecting some simple numbers as answer. I'm not expecting any L'Hopital's rule or anything, So any, yeah. Yeah, but what happens to this term as b goes to infinity? Always? It goes to 0 if, yeah. Okay, we are kind of getting there. S will be greater than a, right? Okay. So this will go to 0 if s is greater than a. Okay, that is a condition that we are going to assume throughout this course. Okay, that whenever we do an exponential function, we are not going to run into convergence issues for this term. Okay, so our s is always going to be greater than a, so that this is positive, and the limit of this term will go to 0. And in that case, this is equal to, as I said, 1 over s minus a, because of this negative and this negative inside that multiplies together. S cannot be equal to a because then that is not defined. Okay. First of all, if s is equal to a, we start with integral of 1 dt there. So s has to be strictly greater than a. Okay. And that's, I think if you look in the table, this is case number 3, right? The third entry. So just so that we could kind of, during problems, I don't have to tell you, oh, it's the 1, 2, 3, 4, just number them 1, 2, 3, 4, 5, 6, so that it's easy to refer. I'm not going to derive anymore. Okay, so I think I showed you how to derive this from scratch. The rest of it, which it should come from the table. Okay. You cannot do chapter 3 without keeping the Laplace transform table next to you, unless you memorize the whole thing, which I wouldn't recommend. So for f of t equal to sine of kt, cosine of kt, e to the power of at, cosine and sine. Okay. And I think there are those resonance terms as well, t sine of kt. And I think I'm missing something, t to the power of n and t to the power of n, e to the power of. All these things are listed in the Laplace table, okay, not probably in this same order, but in some order. Okay. So see table for Laplace transform of this one. So let's get used to it. We need to be able to read it from left to right, and then later today from right to left, which is the more stressful thing. So examples. What is the Laplace transform of cosine of 2t? Just look from the table, okay? I'm not asking you to derive it from improper integral or anything. Look in the table and tell me what it is. It should be case number 5 or 6, I forgot. But yep. S over s square plus 4, and the 4 comes from 2 square. Okay. And what's this case number 5 or 6? 5. All right, let's do a few more. Laplace transform of sine of 7t. And somebody online, look in the table and tell me what this would be. Just unmute and say if you don't want to type it. Don't worry, you're not on national television. Just go ahead and.
Would it be 7 over s squared plus 49?
Good. 7 over, that's k equal to 7, 7 over s square plus 7 square, which is 49, okay, not 14. Number 3, what about the Laplace transform of t to the power of 4? I think this is case number 6. Let me know if I'm not writing the case numbers correctly so that I won't confuse you later. Okay. What do you see if you look at the Laplace for t to the power of n? Yep. All right. So he said 4 factorial. Is that something all of you know, or does it look like an angry 4 to you? 4. So hope all of you are familiar with what a factorial is. Okay. It's just the product of the numbers till that number. So 1 times 2 times 3 times 4, which I think is 24. Okay. I think your calculator should be able to do it. Actually, this is one of those things which you probably wouldn't have been able to do in calculus. Okay, we never had factorial in calculus. Now you have this mysterious thing here, okay, which is kind of discrete. Okay, so we are able to find the individual Laplace transforms. Okay, and don't forget, all these are coming out of this improper integrals. So if you have a combination of these, you should be able to do it. So I'm going to write a property which I'm pretty sure all of you would have done it even if I didn't write it here. Okay. Important. Called the linearity property. So suppose you have two functions f of t and g of t, whose Laplace transforms are given to us. Okay. Be more than two, but if you write two, I think it's easy for 2000 of these. Okay. So suppose these are two Laplace transforms we know, maybe those two which I did earlier, then Laplace transform of a times f of t plus or minus b times g of t equal to a times capital F of s plus or minus b times capital G of s. And there's no magic there, right? It's just like if you take the integral of a sum, it's a sum of the integrals. If you take the difference of two integrals, it's the, or the integral of a difference, it's the difference of two integrals. So that is pretty obvious. Even if I didn't tell you this explicitly, you would have done it. What is not true, again, since we all have a tendency to assume things not in evidence, what is not true, unfortunately, is the following. Again, I wish that was true, but it's not. Because the integral of a product is not the product of the integrals. So if you don't want to write it, don't write it, okay, but don't ever do it. That's the whole point. If you do things like that, I'll be deeply offended, So stay away from those kinds of things. All right, so let's do a couple of examples to make sure that all of you understand the linearity property. Again, we are still having fun reading from left to right. Okay, nothing crazy so far. So example 1, Laplace transform of 3 e to the power of 4 t minus 7 sine of 2t plus e to the power of negative 3t sine of 5t. So there you go. It's a kitchen sink of functions, all kinds of crazy things in there. Okay, so no magic here. So I think this is case number 3. This is case number something. And this is, I think this is case number 6 and 7 respectively. If you were able to number these downward from 1 to 13 or something. Let me know if I'm off by 1 or 2. Say 6 and 7. Okay. So all those table results were obtained by doing integration by parts multiple times, sometimes. Okay. So you don't have to do all that stuff yourself. It's done for you. All you have to do is just copy it correctly. Okay. So the first one is a equal to 4, and that's going to be 3 over s minus 4. It's not s plus 4. A is positive 4, it's s minus a, the denominator. Okay. The second one is going to be plus. The only difference between the sine and the cosine is the numerator. The denominator is the same. Okay. So it's going to be k over s squared plus k squared for sine 2t. It would have been s over s squared plus 4 for cosine 2t. And this one that looks like a damping oscillatory term. Okay, so you can see why these terms are probably going to be useful later, and that's going to be S. I think it's S minus A, which is S minus -3 over S minus -3. That's again S plus 3 whole square plus 5 square, which is 25. So this is your S minus A is -3. For which one? Oh, yes. I forgot. So it's -7 times that. Yes, so it's going to be -14. My bad. Yes, everything that came with the problem should be there. Okay. Yeah, thank you. So are all of you comfortable with reading from left to right? That looks like an easy thing to do. Right? Could have done this in kindergarten. All right, now the backward process. Suppose you know the Laplace transform, how do we retrieve the function? Okay. Suppose we know f of s. So we are in the frequency world. How do we get back the signal that corresponds to that in the time world? Then we can find the inverse Laplace transform. And since I'm going to abbreviate it, let me just give a capital I for it. Okay. Inverse Laplace transform ILT. Denoted by L to the power of -1, just like any other inverse of f of s equal to little f of t. Now you're looking in the second column or the right side column and kind of going backwards. Okay. The only problem is the table cannot accommodate all the functions you know on this planet. Okay. You have to be a little bit creative at times so that you could break this down and somehow get this back. Okay. So this is where all the algebra is going to be required. Writing the table for the functions was easy, but now the result for the Laplace transform may or may not look perfectly like this all the time. Okay, in that case, you have to be careful and be prepared to do some simple manipulations or some algebraic steps to get this process done. All right, so let's do some examples now. If you can get this idea straight, or if you can get comfortable with this process, okay, the rest of this chapter should be pretty straightforward. Okay. Students either like it or hate it based on this step. All right, so let's start with easy ones. The Laplace inverse of s over s squared plus 16. So we need to kind of look at this term and look what is the closest possible entry on the right hand side. Okay. Luckily for us, this is a perfect square, so there's no need to struggle with any bad numbers there. Okay. So we have s over s squared plus k squared. What do you think its inverse Laplace transform would be? So the answer should have a t in it. Okay. This came from s. Yeah. Cosine of 4 times t. Right. What about L inverse of 1 over s plus 7? So this, I think, was case number 5, and this is case number 3. You don't have to write the case numbers when you do a quiz or test, but yeah. E to the -7t. Okay. So one thing I'm paying attention to is, what variable you have in the given function and what you are writing it here. Okay, if you write s here, that's wrong. Now I'm going to throw some curveballs at you. Okay, number 3, L inverse of 1 over s squared plus 9. Okay. This one is not difficult, but you need to be careful. If you look at the table, there is nothing that looks like this. Okay, there is something that is close, but not exactly, right? This is 3 square. So this is almost case number 6. If you had what here? 3. Okay. 3 over s squared plus 9. Then it will be a perfect match. Okay, but that 3 is not there. But we are allowed to bring the 3 in. Okay, as long as you don't do anything to the function, you could do this as 1/3 L inverse of 3 over s squared plus 3 squared. Okay. That is not a huge algebraic manipulation. Okay, you should know that you're always allowed to multiply and divide any non-zero number as you want. Okay. Usually you do it for a purpose. You don't just do it randomly. Here, you're doing it because having this 3 here is useful. So you multiply and divide a 3. And this is now a perfect match with case number 6. Okay, that's going to be 1/3 sine of 3t. So just keep a list of the different manipulations that you would need. Okay, multiplying and dividing a non-zero number. Okay, you cannot multiply and divide an s there. Okay, that is not a number. You can divide a number, and again, don't multiply and divide 0. Okay. All of you understood why I did that, or it's not too bad. So find the Laplace inverse of s over s minus 2 whole square plus 25. So I'm expecting it to have some twist, okay, but not it's not a terrible thing to do. Now this is a close match to which case? Almost case what? Almost case 7. Okay. The exact case 7 should have looked like this: s minus 2 over s minus 2 whole square 25, which is 5 square. Okay. This is what case 7 should have looked like. Okay. We don't have that s minus 2. How do we make this happen? If you don't have a number which is in this position, okay, can you just bring that in and somehow undo it at the same time? Just like I did the multiplication and division, is there a corresponding thing here? Subtract and add 2. Okay. It might look like a silly thing to do. So you can subtract a 2, add a 2. Okay, I haven't changed anything. Divided by s minus 2 whole square plus 5 square. Okay. You should be comfortable with these kinds of things, okay, over the next couple of weeks. Okay. Now what do? Kind of group it and split it into 2 terms. Okay. So we have L inverse of s minus 2. Don't cancel the 2 and negative 2. Okay. Then we are back to square 1. So keep this as one term. And then you have plus L inverse of 2 over s minus 2 whole square plus 5 square. Okay, so not only can you divide and subtract, not only can you divide and multiply a number, you can also subtract and add, or add and subtract a number as you wish. Okay. The whole point is to not change the function at the end of the process. Now this is case number 7 exactly, right? This one is probably not what you need, okay, but you know what to do in such situations, you know. This is almost case number 8. If you are doing exactly case number 8, it should look like this: 5 over s minus 2 whole square plus 5 square. So whenever it's almost, just take it to the side and see what you can do with it. So the first one is a perfect match. So it's going to be e to the power of at cosine of bt, or cosine of kt. That's going to be cosine of 5t. So a is 2, k is 5, a is 2, k is 5. And this one, to get the 5 up there, you will divide and multiply a 5. That way, this 5 is sitting here, and you have to, of course, divide a 5 so that you don't change the function. So it's going to be plus. This 2 is an unnecessary commodity here. Just take it out, okay, because the 2 is not helping anything. So pull that out. You only need 5 to make it a perfect match to case number 8. Okay. So this 2 and the 5th that you divided here makes it 2/5 e to the power of 2t sine of 5t. The whole point is to get an exact match, okay, no matter what it takes to get it, okay, whether it's multiplying and dividing or adding and subtracting. When you add and subtract, okay, this is almost always a requirement that you have to split it into 2 terms, okay, so that you get a cosine and a sine, and then you could do manipulations later if needed. To some of you, it might look a little surprising that, you know, these things are needed, but we'll get used to it. Don't worry. Okay. Don't get scared or anything. This is a simple algebraic manipulation. Any questions on this? Now let's make it worse. Example number 5. L inverse of 1 over s square plus 3s plus 2. When you get an expression like this, okay, and this is why the first lecture is always a little rough. We have to kind of go through a thought process. Okay. The first question is, can we factor this? The answer is yes. That's good news. Okay. The answer is no. I don't say that's not good news, but the answer is yes. Okay. Let's just go through that route so that we could make use of some familiar algebraic techniques. Okay. So the answer is yes in this case because it's s plus 1 times s plus 2. That's going to be L inverse of 1 over s plus 1 times s plus 2. Remember that, you know, we cannot take the individual Laplace inverses of these two and multiply them. Okay, that is not an option. And there is no such thing in your table. If you look from the first to the last list of things I have listed there, okay, you cannot get something like this. My question to you, which I've asked you on the very first lecture, how do we separate a product of terms like this into 2 individual terms? Yeah. Partial fraction. Okay, get ready now. This is the one of the million times you're going to do this. Okay. Told you it was coming. You cannot do Laplace transform without partial fraction. Okay. So you can do it on the side or you can do it inside, wherever you like. So 1 over s plus 1 times s plus 2. If both these are linear terms, which means you could write this as a constant over s plus 1 plus a constant over s plus 2. For cases like this, you could just cross multiply and clear the fractions. So it's going to be 1 equal to a times s plus 2 plus b times s plus 1. And using this popular technique called the Heaviside's cover-up method, which means you just hide one term at a time and figure out the other one. Okay. So s equal to -2, for example, will give you the second term. So b is going to be equal to -1. And similarly, s equal to -1 gives you a equal to 1. It's called the Heaviside's cover-up method, which is something that an engineer developed. So it has got some mathematical weaknesses in it. Okay. Keep in mind that you really cannot plug in s equal to -2 and -1 into this. They are not defined there. So it's kind of a escape route to just do this problem. Okay. But it works. That's good news. So it's equal to 1 over a is 1. Yep, 1 over s plus 1 minus 1 over s plus 2. This is the only way to find the Laplace inverse of that function. Okay, you need to separate it out into two terms and then use the linearity property. Okay. So the L inverse of this would be the Laplace inverse of 1 over s plus 1. The linearity property applies both ways, okay, back and forth. So it's L inverse of 1 over s plus 2. Which I think both are case number 3, and this is equal to e to the power of -t minus e to the power of -2t. Remember, the given Laplace transform was in the frequency world, you're transforming it into the time world. So if you've never done partial fraction, if you forgot it, take some notes so that you know which cases we need for this course. Okay. This is the most fundamental case where you have two terms of degree 1. Okay, this is always the structure. Any questions on partial fraction? So I want to make sure all of you are comfortable with this. Okay, this is super important. Let's do a few more. 6. One divided by s minus 2 times s squared plus 36. There is a linear term and a quadratic term in the denominator. Okay, so I'm doing all different cases today so that you are prepared for the future sections of this chapter. We need partial fraction. Okay, whenever we have two terms multiplied, the only legal way to separate them is to use partial fraction. Okay. And this is where I want you to be careful. So we have 1 over s minus 2 times s squared plus 36. This one is a linear term, okay, nothing confusing there. How do you write the partial fraction thing for s squared plus 36? Yeah, good. So it's bs plus c. Okay, it depends on the degree of the term here. If it's a degree 2, that must be degree 1. If there's a degree 3 here, let's write a quadratic here. Okay. So it's always 1 degree lower than the denominator that you're writing up there. Okay. So please don't make a mistake with this. Okay. That's going to lead into all kinds of disasters. Just keep your focus on what you're doing when you do problems like this. It's not b over s squared plus 36. Okay. So once again, clear the fractions. So 1 equal to 8 times s square plus 36 plus s minus 2 times bs plus c. You won't be able to get all these three things just by the cover-up method. Okay, unfortunately, you have to do something more here. When the factors are both linear, it's very convenient. You could just cover up one at a time, get those a and b. Okay, here, this expression is never equal to 0. Okay, some students think that plugging in -6 there makes it equal to 0. It's not. Okay, this is not equal to 0 for any real value of s. So the only thing you could do at this point is to plug in s equal to 2. Okay, that is an option. And that gives you 1 equal to 8 times 2 square, which is 4 plus, that's 40a. So a is 1 over 40. Okay. What do you do for the remaining two letters, B and C? There's only one way to do this. What is that? S equals 0. That will still leave both. Yeah, you could do that. S equals. But why did you choose S equal to 0? Okay. So his suggestion is to put S equal to 0, okay, so that we can kill that B term and just focus on what we have. That gives you 1 equal to 36a plus -2 times c. And you know a is 1 over 40. Okay. Not the most pleasant of the numbers. That's okay. So 2c equal to 36 over 40. C equal to 18 over 40, which is 9 over 20. Let me know if I'm making any arithmetic mistakes. Is that okay? And how do you find the value of the remaining letter B? Yes, you can plug in any random number. So s equal to 1 maybe. Okay. You can plug in s equal to 37, but that's going to make it worse. So s equal to 1 is probably the easiest number, or -1. I don't know. So it's going to be 1 equal to 30. Oh, 37 appears anyway. 37a. And you have 1 minus 2, which is -1 times bs plus c. That is what you want. So it's minus b times s is 1 and c is plus 9 over 20. And a is 1 over 40, so this is 37 times 1 over 40 there. And 9 over 20 is 18 over 40. And 1, of course, is 40 over 40. So if you do all that fancy adding and subtraction of fractions, you get 21 over 40 with a negative. Sorry for all the bad numbers. I didn't plan the problem properly, so you have all these fractions which are kind of hideous but not too bad. So a is 1 over 40, b is -21 over 40, and c is 9 over 20 or 18 over 40. Okay. So let's write down what we have, the fruits of our hard work. L inverse of a over s minus 2, which is 1 over 40 over minus 2 plus bs plus c, which is minus 21 over 40 s over s square plus 36. So it's b s over the denominator plus c, which is plus 9 over 40 1 over s square plus 36. Writing those terms in a way so that those fractions don't really hinder my calculations later. Okay, it's up to you, whatever helps you, but this is my b, this is my c. All right, now I think we are ready to attack this term by term. Okay, this is looking as a perfect match with case number 3. This one is a perfect match with case number 5 or 6. S over s squared plus case 5. And this is almost case number 6. Okay. And to make it a perfect case number 6, you just divide and multiply as 6. Okay. Now that we have done it once, you should be able to just do those manipulations as needed. Okay. So there is an extra 1/6 that comes with this already existing fraction. Okay, now let's invert it. That's going to be 1 over 40 e to the power of 2t. Okay. S minus a is going to be e to the power of 8t minus 21 over 40. This is a simple oscillatory term. It's just cosine of 60. Okay. Plus this beautiful fraction, which is 9 over 240 or 3 over 80. Is it? Plus 3 over 80 times, I won't get upset if you don't reduce it to the lowest fractions, sine of 60. That is your final answer. So you can see things are getting a little bit complicated here in terms of all the, okay, so we had partial fractions and then we also had to do this small manipulation here. For s equal to 0, wouldn't c come out with negative 1 over 20? Was that the case? I hope not. Let's see, so c s equal to 0. We have 1 equal to 36a plus negative 2c. Did I mess up the whole thing? So we bring 1 over 40 there. Gotta be kidding me. Can I just go back in time? Forgot this 1. Is that what happened? All right, so that's 1 minus 36 over 40. Thanks for pointing that out. Which is what? 4 over 40, which is 1 over 10. Sorry for all the extra work I'm creating here. 1 over 10, 4 over 40, and that changes this thing here, which was 4 over 40. So that's going to be 4 over 80, that's 1 over 20. Yep. I need to write better problems now. So this is 4 over 80, okay. This is 2 over 40. Sorry for this confusion. So this is 3. So B is what? B goes there. here. Negative 5 over 40. I should 3 over 40 equal to negative b minus 2 over 40. Bring the b here, bring this thing here. What happens if I don't write all the steps? That's negative 5 over 40, right? Okay. And then what else is there? We have everything. Okay. So this should be minus 5 over 40. And C is positive 1 over 20. Times this, it's going to be plus 1 over 120.
Sorry, Professor. I think
Okay.
C is negative 1 over 20.
It's a everlasting problem. Eh? Keep missing one or the other. So did I miss a negative? Oh. Luckily, we have some time to waste. So did I fix that one now? Equal to this and this negative b plus 2 over 40. And then you bring the b there. This is negative 1 over. Is that right now? All right. So negative 1 over 20. Negative 1 over 120. So my first mistake was that I forgot this 1 there, and then I forgot this negative. So two mistakes that kind of caused all this extra stress. Sorry about that. And thanks for being observant there. What will I do without my online crowd? Okay, so that is the answer. What's that? Oh, I see. I didn't update that yet. Thank you. Did I change everything else? Because I start off with the wrong answer, so I need to be careful about updating everything. One last example. Okay, this is just to kind of remind you of some of the nuances in partial fractions. This is example number 7. L inverse of 1 over s times s minus 2 whole square. This is what you call as a repeated term. Okay, be careful about these creatures here. Partial fractions have separate cases depending on what your denominator looks like. Okay. So the case with repeated factors, if you have never seen this in high school, please make a note of it. So if you have something like this, 1 over s minus a to the power of m times s minus b to the power of n Okay, just two cases for the time being, could have more terms. Okay. You need to give a term for each of these number of times it's multiplied. So a over s minus a plus b over s minus a whole square plus c over s minus a to the power of 3 until you reach the value of m, whatever that m is. Okay. So plus whatever, let us say k over or m over s minus a to the power of m. So if m is 5, you would stop at 5. If m is 17, you would stop at 17. And do the same with n with a different set of constants. So it's going to be a1 over s minus b plus b1 over s minus b whole square and so on. Okay. So that is what you would do for repeated factors. It's not a common occurrence in chapter 3. We will see one or two problems here or there. Okay, just don't assume that this is a quadratic, so you could do it like the previous one. So this is going to be the L inverse of 1 a over s plus b over s minus 2 plus c over s minus 2 whole square. Because s minus 2 is repeated twice. Okay. So you have to give it once and twice. And the numerators are all linear. I'll do this or finish it off tomorrow, okay, but try to just see if you can do the ABC part for this, okay, just as a small exercise later today. In the meantime, again, my apologies for the mistakes up there, okay, that was not intentional. Test 1 this Thursday, test 2 on 5/27 on chapter 2. And there is no lecture next Monday, so after the test, you could have a long weekend. All right, I'll finish this off tomorrow when we start. All right, I'll stop recording this lecture. And if you have any questions,